Okay, so just a little video to finish talking about magnetic force. So what we're looking, there are a whole bunch of different types of magnetic forces, or between different things, like between two magnets, between a current and a magnet, between two currents, between a magnet and a moving charge. And we're going to look at all of them. Actually, I said between two magnets. That's the one that we don't really know the answer to yet. We don't know the formula for. We know that it should look like the inverse square law, the Fg equals gmm over r squared, and the Fq equals kqqq over r squared. But we haven't been able to find it for magnetism because we haven't been able to separate the two poles. So we're sure that it acts like what's called an inverse square law. We just don't know what these two things on the top would be because we haven't been able to separate a monopole. Like right now we have dipoles, like the north and the south are always together. And because of that, we also haven't been able to find the constant. And it will be our next lab where you will see that the force or the magnetic field will go as something over r squared. We just don't know what's on the top. So we'll get back to that one. So today we're looking at a current carrying wire and a magnetic field. Okay? And we said just before you left, so if we have the magnetic field, I'm going to draw the wire in here and the magnetic field around it. We said that the things that it should be dependent on, so this field's going into the board and the current's going upward, let's say. So we said the things that the force on this wire should be dependent on are, one, the strength of the field, and the stronger the field, the bigger the force. Two would be the current flowing in the wire, and the bigger the current, the bigger the force. Three would be the length of the wire in the field, and the longer the wire, the length of the force. And the fourth one is the angle that the wire is with respect to the field. So the angle between field and wire. Okay, so what are we looking for? We're looking for force, and we said the bigger the strength of the field, the bigger the force. So it's going to be on the top. Bigger the current, the bigger the force. It's going to be on the top. Longer the length, the bigger the force. So all of these are going to be together. And then we said there's an angle here, and it has to be sine because it's being cross multiplied. So the actual equation is F is equal to B cross IL. But that means it's equal to BIL sine theta. So we're cross multiplying. So this is our equation, and it's often known as the Bill equation. So where B is the magnetic field strength, measured, of course, in Teslas. I is the current in the wire. Measured, of course, in amps. L is the length of the wire. Measured in meters. And theta is the angle between the two vectors, between B and I. Okay, and because it's sine theta, you're going to get the biggest force when they are perpendicular, and you're going to get zero force when they're parallel. So this will give me the biggest magnitude of force. If the wire was running with the field, like into or out of the board, it would be zero. All right, now, and then F then is the force between wire and field, or the force that the field is putting on the wire. On wire. Now, this is actually the equation. Our Bill equation is actually the equation that where we define a Tesla, right? Because I told you from the B equals mu OI over 2 pi r that field was measured in Teslas. But what's a Tesla? It's not one of the 7 fundamental units. So if you rearrange the Bill equation for magnetic field strength, it'll be F divided by IL, and the sine theta doesn't have a unit. Okay, which means it's a Newton over an amp meter, and that is what we rename a Tesla. Okay, so a Tesla is a Newton over an amp meter. Remember from maybe Physics 11, maybe from earlier in this semester, there are 7 fundamental units in all of the metric system that every other unit is made up of. And I don't remember which half of the class I talked to these about, but they are a meter, a second, a kilogram, a mole, a degree Celsius or Kelvin, depending on 1, 2, 3, 4, 5. And another one is an amp. An amp is a fundamental unit. We remember we found amp by saying Q over delta T, but really an amp isn't a coulomb over a second. Really, a coulomb is an amp second. So it's a fundamental unit. And the third one you probably won't ever see in physics. It's called a candela, and it's a measure of light intensity. Okay, so every other unit really can be broken down into some combo of these. So a Newton is a kilogram meter per second squared, an amp is a fundamental unit, and a meter is a fundamental unit. Tesla is not. Okay? Now, one other thing, this is a vector. And because it's a vector, it means there has to be a hand rule. So if we go back to this question, the hand rule goes, with the appropriate hand, point your fingers in the direction of the magnetic field, so they'll go into the page. Point your thumb in the direction of the current flow, and the force will come out of the palm of your hand. And actually, that's an electron, so I need my left hand. Fingers in the direction of the magnetic field, force in the direction, or thumb in the direction of the current flow, and the force comes out of the palm of your hand. And in the next video, I say it so you can write it down. But the force comes out of the palm of your hand, kind of like a Spider-Man thing. So for this one, the force would be going this way if you use your left hand. You know how the webbing comes out of the Spider-Man's hand? Or if you're into Iron Man, the force comes out of Iron Man's hand, which seems to be appropriate since we're doing electromagnetism, iron. Okay, so this one's called the right hand / left hand palm rule. And in the next video, I do go over it and get you to write it down. Okay, but it's based on this equation, which you're going to use for your homework for Tuesday night. Okay, very good.